In this lesson, we look at diffraction gratings, and here are the objectives. In previous lessons, we've shown light through a single slit and seen the diffraction pattern, and through a double slit setup and seen the interference pattern. And now what we're going to do is just keep increasing the number of slits and see what happens as we shine light through that. So a diffraction grating is something that has very many narrow parallel slits, and we're going to shine light through it. And when I say very many, we're going to get up to the order of thousands per millimeter. And we'll see what happens as we shine light through that. Let's take a look at a simulation. So once again, this is the multiple slit diffraction pattern simulation from the Wolfram Demonstrations project. We looked at this in a previous lesson. And here we see the single slit diffraction pattern. We have chosen one slit and it has a finite width. And here we see that pattern. And we've already seen that if we move to two slits with a finite width, we keep this same outer envelope, but now we have the double slit interference pattern that is within that envelope. And now what we'll do is we'll just keep increasing the number of slits and see what happens. Now first of all, I'm going to actually zoom in on this a little bit so that we're just looking at the central maximum to make it a little bit easier to see. So I'm just zooming in, and that's what this is doing. And now what I'm going to do is I'm going to move to 3 slits. And there's a bit of a lag in the simulation, but you'll see what happens each time. And then 4 slits. And notice that the location of the maxima is not changing at all, but they're getting more defined. They're getting sharper. What that would look like on a screen is that the edges are getting clearer. And we would see the maxima actually getting a little bit brighter. Although the intensity is not changing here, it's all relative. As I go to more and more slits, we're getting these more and more sharply defined maxima. Notice that there are these little secondary maxima in here as well that are smaller. And if you go back and rewatch the simulation, you'll see there's always 2 less of those secondary maxima than the number of slits. So when we have 5 slits, we have 3 of those secondary maxima, 10 slits, we have 8, etc. And if I skip all the way up to 10, we get the sharpest maxima yet. So I'll let it get to 10 here, and then I'll go back to 2. Notice that the location of the maxima doesn't change as I swap between the two of them. So now in a moment, it'll go back to 2. They don't change their location, they just get more sharply defined. So this now, with 10 slits, is a kind of diffraction grating. And we could increase the number of slits even further, and we would see greater and greater sharpening of the maxima. So as the number of slits increased, we saw that the location of the primary maxima, those big sharp maxima, that doesn't change. However, the primary maxima themselves become sharper. And although we couldn't see it in the simulation, they also become brighter. As you have more slits, you're letting more light through in total, so they get brighter. Now, we won't go through a full derivation of this, but here is a very similar setup to what we've seen in previous lessons with the single slit diffraction and double slit interference patterns. Here we have the barrier, the light's coming in from the left, and the screen is far off to the right. And it's so far away that these light rays are effectively parallel. Now, as we've seen in previous lessons, we can draw a little triangle here that's a right angle triangle, and this is our path difference. Now, if we imagine that over here we're going to the wall and we're going to have constructive interference, then this path difference must be, for the first one, must be 1 wavelength. Now, if I continue this triangle and we get a similar triangle here and here, this would turn out to be 2 wavelengths, and this would turn out to be 3 wavelengths, again by similar triangles, just to show you that the overall geometry doesn't really change. These are all going to still interfere constructively, so we have a similar sort of thing as the 2-slit interference pattern. And therefore, the path difference equation is the same one that we saw for 2-slit interference, namely that n, which is an integer multiplied by the wavelength, is equal to d times sine theta. D, again, is the distance from the center of one slit to the next. Theta is the angle from the line through to the center there, like it has been in previous derivations. And n we call the order, and it's an integer. It starts from 0, that would be the central bright fringe, and then 1 would be the one to the side, 2, etc. And just to note that unlike the 2-slit interference pattern, we can't simplify this further with the small angle approximation to get another equation. We have to use it in this form because the angles can get quite large as we go out to the side when we're using a diffraction grating. The pattern that we'll see on the screen now is these brighter, sharper fringes with a more dark area in between. And this would be the central one for n is equal to 0, then n is equal to 1 on either side, and n is equal to 2. And right now in this example, we're shining monochromatic red light through there. If we were to take blue light, blue or violet, which has a shorter wavelength, we're going to have less of an angle of deviation. And so the blue light would be in here, like that. So this would be n is equal to 1, and this would be n is equal to 2, and that would be the same on both sides. And the blue or violet light at the center would end up in the same place. So different wavelengths of light have different angles of deviation, because if you change the wavelength here, you change the angle here, so they end up in a different location on the screen. And you can imagine then that if you shone white light through here, you would get a white central fringe as all of the colors stack up like this. But here you would have a spectrum from violet on the inside to red on the outside for the first order, and then violet on the inside and red on the outside for the second order, etc. So we can use this to separate out white light. And just to show you what that would look like, looking from overhead, here's our diffraction grating, white light coming in from the left, we'd have a white central fringe here, so I'm going to draw this with a black outline. This would be white, and then we would have, for the first order, the violet on the inside on both sides, like this, and we'd have the red on the outside, like that, and a spectrum in between, which I don't have enough colors to draw, but imagine all the other colors in there. And then we would move to the second order, and we would have violet again, like this, and red on the outside of that as well. Continuing and continuing. So diffraction gratings are used in spectroscopy. Spectroscopy is the separation out of light into different wavelengths, and they're used like prisms to disperse light, for example from stars. And that's useful because different elements absorb and emit different wavelengths, as we'll see when we get to emission and absorption spectra in a later lesson. And therefore we can actually use this to tell the composition of the stars in the stellar atmosphere. So by capturing light from faraway stars and passing it through a diffraction grating, astronomers can separate out that light into different wavelengths and look for the characteristic wavelengths that are emitted from certain elements, and as a result they know what elements are making up those stars that are many light years away. One last thing to look at here, and that's the resolvence of diffraction gratings. So we've seen that the more lines you illuminate in a diffraction grating, the more sharply defined are the maxima that you get. So there's a measure called the resolvence, which we give capital R here to, and it's a unitless measure that is telling us how well a given diffraction grating is able to separate out wavelengths of light that are close together. So lambda here is the wavelengths of light that we're looking at, and delta lambda is the smallest difference in wavelength that we can tell apart. So it's the smallest difference in wavelength that we can tell as two separate lines in the spectrum that we see. M here is the order, so we're using lowercase m instead of lowercase n, but it means the same thing, 0, 1, 2, 0 being the central, bright fringe, etc. And we're using m because we've got an n right here. And n, capital N, is the number of slits illuminated. So if we rearrange this then to solve for delta lambda, that's again the smallest difference in wavelength that we can observe, that we can tell is a difference, then we get delta lambda is equal to lambda, the wavelength that we're talking about, divided by m, that's the order that we're looking at, multiplied by n, the number of slits. And that tells us that if we want to discern a very small difference in wavelength, we want to be able to tell that two very close together wavelengths are actually separate and different, then we want this number to be very small, which means we either want this number or both to be very big. In other words, we need to look out from the center bright fringes towards the higher order fringes, and we also want to illuminate a lot of slits. Let's take a look at an example to help make this clear. If we heat up sodium to a very high temperature, or we expose it to a very high potential difference, then we can get it to emit light, and two wavelengths in the spectrum of that light have a wavelength of 589 nanometers and 589.6 nanometers. So those are very close together. The difference between them, delta lambda here, being equal to 0.6 nanometers. And this is a classic test for how good a diffraction grating is. Can it see these as two separate lines in the spectrum? So we're asked to find the number of lines per millimeter needed in a diffraction grating if we're to resolve those, meaning see them as separate and distinct, in the second order spectrum. So this is telling us here that m is equal to 2, and here these are the wavelength, and we've said that the difference in wavelength is 0.6 nanometers. So if we start from our equation, then we can rearrange that to solve for n, the number of slits that we need to illuminate. And here we have a bit of a choice as to this value. So we could use 589, 589.6, or the average between the two. It's actually not going to make a difference in our answer, so I'm going to use 589 times 10 to the negative 9 meters. And that's divided by, we said that we're looking at the second order spectrum, so m is equal to 2, and the difference we said was 0.6 nanometers. And if I do that arithmetic, I get that I need to illuminate 490.8 lines, and we've said that that's in 0.1 millimeters. So in order to do that, I need 4,908 lines per millimeter, which is approximately 5,000 lines per millimeter to answer the question asked at the beginning. And that's a pretty standard number of lines per millimeter for diffraction grating. So that's an introduction to diffraction gratings, what they're used for, and also their resolvents.